welcome to this first seminar in a series of research seminars hosted by Nomadic Labs. Today's speaker is Christopher Goes. So Christopher Goes is one of the co-founders of the decentralized protocol research and development company Metastate. He focuses on type theory, zero-knowledge cryptography, and crypto-economic systems design. And in a previous life, he used to program underwater robotic submersibles. But today he's here to talk about Juvix, a functional smart contract programming language for Tezos based on state-of-the-art type theory. So over to you, Christopher.
Thank you. Thanks everyone for coming. I am excited and a little bit terrified to be giving the first research seminar. I seem to have been elected as the guinea pig, but I will try to do it justice. Thank you for the excellent intro. As mentioned, I work at Metastate, but all work in this presentation, it's not just my own, it's also joint work by the Juvix team and some even by the cryptography team at Metastate. The Juvix team consists of Marty, Jeremy, Andy, April, and myself. So, what will I go over in this talk? First, I'll give a quick background, explain why we chose to pursue this problem in the first place, and briefly introduce Metastate, although I expect most of you have heard of us already. Then I want to outline the process we went through in choosing to design Juvix the way we did and give a sort of broader rationale for the landscape of smart contract languages, what different trade-offs are, what different approaches are, especially to formal verification, and what approach we've chosen to take with Juvix and why. Once I've talked about why we took that approach, I'll outline how we actually have gone about implementing it in 5 main components of Juvix: the Frontend Language, the core quantitative type theory, the Michelson backend, the arithmetic circuit backend, and then the proof UX research. That will be the bulk of the presentation. Finally, I'll talk about the status of the project, what's ready, what's researched, what's implemented, what can you use, if you are feeling particularly adventurous, could you dive in and figure out. And I'll provide some links at the end of the presentation to further resources, papers, code, documentation, and etc. that you can consult. It is always a little tricky to give. I have not quite got used to the online presentation thing because it feels like I'm talking to my laptop. My laptop is this inanimate object which does not respond. I am told that questions will be relayed. If you have questions during the presentation, please feel free to send them in the event chat. And I think ones may be relayed backstage. I'll take a look every 5-10 minutes or so, just in case I didn't explain something particularly well, then I can go back to it. There will also be a time allocated for questions at the end, and if we don't get to all of them within, I think, 15 minutes, technically, because this event ends in an hour, then I will be more than happy to take questions over email or other communications channels, as long as you have them. All right, quick background. So I did not start working on distributed ledgers from the crib. Most of my life was spent doing other things. In a previous life, just mentioning it because it is a little bit interesting, I worked on robotic submersibles, mostly in college, programming autonomous submersibles, which had to go around and do various tasks. Unfortunately, it turns out that autonomous submersibles are mostly used by the American military, and they mostly go around the seafloor in a very geometrically regular pattern and don't do anything interesting, autonomous or economic, game theoretically or otherwise. So I switched fields, and I've been working in DLT for a little over 2 years now. I'm particularly interested, as I'll get to a little bit more in more detail when I talk about the design approach behind Juvix. I'm particularly interested in both privacy-preserving digital infrastructure and dealing with coordination problems and legibility of resource chains, which I think distributed ledgers provide some compelling tools to address. So I work for Metastate. Metastate is a protocol development company headquartered in Switzerland, although, of course, all of our employees are remote and there is not much of a physical office presence at this point this year. Metastate was founded on the thesis that blockchains don't quite work yet, at least not in practice, and that technological lock-in effects leverage early influence a lot. So it makes sense to, it's of the right time now to start thinking about the long-term implications of the technical design choices we make and making the right technical design choices early on. As an example of a case of technological lock-in effects where the wrong design choices were made, I would point to JavaScript, which was originally intended as a very simple language to manipulate minor elements on HTML web pages and turned into this gargantuan, impressive, but perhaps not quite so elegant tool of dynamic web programming. So we're aiming to do a little bit better than JavaScript, but also leverage the same kind of lock-in effects to assent the course of distributed ledgers in a good long-term direction. Metastate focuses on Tezos core engineering, all of the recent protocol upgrades in collaboration with Nomadic and the upcoming ones as well, programming language theory and cryptography. Mostly I'm going to talk about the latter two areas in this presentation, mostly programming language theory, but I'll touch a little bit on cryptography as it applies to Juvix. So, design rationale. Why a smart contract language and why Juvix? Smart contracts have three, lots of characteristics, but three particularly salient ones. They are security critical. They're often manipulating large quantities of funds or manipulating valuable assets or state transitions which otherwise represent something that can convey force in the world. They are performance sensitive because smart contracts are being executed, generally speaking, in replicated fashion on a distributed ledger. That replicated execution must be paid for. And so any inefficiencies in your contracts result in your users needing to pay more money and the validators needing to perform unnecessary computations. And smart contracts are finally, at least historically, very bug prone. The most, of course, famous examples have generally occurred on Ethereum so far. And there was the DAO back a few years ago. Then more recently, I guess in the middle of the parity multi-signature incident, and perhaps more recently, over the summer, I have not been paying too much attention. I just get sort of a service feed from my Twitter account, but lots of DeFi contracts, which in many cases, not only were they not secure, they weren't even audited before people sent funds to them, and have often resulted in a loss of funds. Now, I'm a little bit less concerned about, in the long run, speculative DeFi Ponzi schemes, although there are also serious DeFi projects. Security-wise, there will always be those. But I think in order to allow well-designed but really genuinely complex projects like the DAO or like a complex authenticated multi-signature or like, say, a stablecoin like Maker, those have sound logic in theory, or at least understandable logic, but translating them into a contract can easily introduce bugs. And so when I talk about addressing bug-prone smart contracts, I'm talking about dealing with serious use cases which are already well understood sort of in abstract theory and some protocol design, and then correctly translating them to a contract. Another characteristic of smart contracts is that security through obscurity doesn't work at all. Oftentimes, companies which can firewall their servers or which can impose an API boundary between users and the software systems they're interacting with can rely on at least some degree of security through obscurity. The users can't see the code, so the potential hackers can't see the code, so they can't exploit any bugs. But smart contracts are in general public and cannot rely on this. But there are trade-offs, I think, in the smart contract language design space, or at least in the design space of what people want to use languages for. So and you could try to balance those as best you can and support different things, but some general trade-offs to consider are a trade-off between the speed of deployment and iteration. So, for example, it's very quick to write a contract maybe in a simple imperative language without any proofs or without any verification, and it's quick to iterate, but it's tricky to verify. And if you include more verification expressivity, that generally requires imposing constraints on the programs which programmers can write. So expressivity of verification may come with some trade-off in the speed of deployment and iteration. Another trade-off is between, between maybe the first two in combination and toolchain complexity or degree of dependence on the compiler. So if you want a very simple compiler that you do not want to trust very much, then you are more limited in the kind of verification you can do or the kinds of translations you can perform on behalf of users because you don't want to rely on your compiler. Whereas if you allow more complexity into the compiler, you could provide perhaps more expressive verification while maintaining performance, but you introduce correctness dependency on your compiler. So Juvix takes a very particular position in that trade-off space. And I'm going to explain now what it is by talking about a few different approaches, especially in the Tezos ecosystem. So if you have a sort of multi-layer smart contract stack where there's a virtual machine running on a blockchain and there are higher level languages that compile to it, then there are sort of there's a bifurcation. There are two paths you can take towards verification of contracts. You can perform verification at the VM level, so at the lower level of the thing with the code which the blockchain is actually executing. So on Ethereum, this would be the EVM, and on Tezos, it would be Michelson. Or you can perform verification in the language itself, and then rely on the language to translate the semantics of the language, which are the semantics that are being verified, to the semantics of the backend VM correctly. And these approaches are complementary. So some specific projects that perform each approach. In the case of verification at the VM level on Tezos, which is actually probably the furthest advanced the blockchain ecosystem, as far as I'm aware of, in this problem. Nomadic Labs has been working on Metastate, which I think has already been used to verify several actually deployed Tezos smart contracts. The Metastate works by expressing the semantics of the Michelson interpreter in Coq, and then this allows you to write Coq proofs to verify contract behavior. Now, the huge advantage of this approach is twofold. One, you're working with the code that the blockchain is actually executing, and two, you don't need to rely on some custom compiler. At least Coq, although it might have bugs, is pretty well tested by lots of people. However, this requires that you perform verification at the level of Michelson instruction sequences themselves. So if a developer is writing in a higher level language and compiling to Michelson, they can't verify in the high level language. They need to take the output of their program and then verify that. And that is much more onerous, potentially, if we're talking about a large program with variables, because this verification has to operate at the level of Michelson stack semantics, stack transformations, stack positions, etc. And it's also, you also have to sort of translate, you're verifying the relations between the input and output storage, but you have to translate those relations to the, say, variable names or data structures you actually care about in your code. So there's a translation there that the programmer has to make, which is also an opportunity for introducing mistakes, but definitely a useful approach. The closest analog on Ethereum to this, I think, is the K-EVM work by runtime verification, which uses a different formalization, the K framework, but is operating similarly at the level of the blockchain virtual machine. So the second main approach is verification in the language itself. This is the approach Juvix takes. There's one prior work here, which I wanted to mention a few years ago, which was an interest backend targeting LLL and EVM by Edstrom and Pedersen. That, similarly to Juvix, performs verification in the higher level language and then compiles it to the backend. But because they were working with interest, which is not designed for smart contracts, and because of several layers and the expensive memory management, which they had to perform on the blockchain, that ended up being much too inefficient for any of those contracts to actually be executed. So this is one reason we've chosen to engineer Juvix as a full stack compiler, as opposed to just writing an interest backend or an agda backend or something. We really need control over all of the compilation passes and performance choices, because smart contracts are quite different than, say, what interest or agda would usually target. So I want to emphasize that these approaches are complementary. They're not really, I mean, maybe you choose to do one or the other for specific projects, but you could also do both. So to give a quick primer on the kind of verification that dependent types provide, and this applies Coq and the type theory used by Coq and the type theory used by Juvix are slightly different, but they're pretty similar in the ways in which you would use them. And broadly, they're similar in the levels of expressive power. It's helpful to talk about different levels of expressivity. So if you have a very simple, like a simply typed lambda calculus, you just have terms which can depend on other terms. So you have some function, it takes an input, and it returns an output, and the output term is dependent on the value of the input term. Then sort of another axis in the lambda cube, so to speak, is where terms can depend on types. That would be system F. If you have additionally types depending on types, that would be system F omega, GHC core. So lots of functionalist languages use a modified version of this. And then if you have all possible dependencies, so terms depending on terms, terms depending on types, types depending on types, and types depending on terms, that would type systems fall into that category, include the calculus of constructions, which is the basis for Coq, and Martin-Lof type theory, which is the basis for agda interest, and Juvix, also referred to as impredictive type theory. So dependent types, because you can allow types to depend on terms, then you can make use of the Curry-Howard correspondence to write proofs, basically, about the behavior of your program. So if you take the types as representing or corresponding to theorems and terms as corresponding to proofs, then you can habit a particular type to prove a theorem. So concretely, let's say you have a smart contract with some input storage and output storage, and you want to prove that it will respect some invariant. You want to prove, for example, that the supply of a token is conserved. Then you would construct a type which expresses that conservation, like supply input storage equals supply output storage. And you would construct a term which is a proof that inhabits that type, and is a proof that that theorem is true. So that term would have to go through the various execution pathways, basically. So if you had like a case statement in your token contract or some sort of branch based on the input value, your proof would need to go through the different branches and prove that all of them satisfy, this sort of thing. Dependent types are quite general. They're the basis for modern proof assistance, Coq, Intersagda, and pretty much anything you would want to prove about a smart contract. You can, in principle, prove. Whether it's easy to prove it in terms of number of lines of proof you have to write, or how easy it is to find those lines, that I'll get to in a later part of this presentation. But in principle, they have all the expressive power we need. So why choose dependent types, and why do it from scratch? I've talked about the expressive power, but the other choice which Juvix makes is to write a full stack compiler. So users, when they're writing proofs in Juvix, they're writing proofs in the Juvix frontend or core language. They're not writing proofs in or about Michelson. So this means that it's easier for developers to write proofs because they can reason about the semantics of this higher level language directly. And it's the compiler's responsibility to perform the translation. But this also means that users are reliant on the Juvix compiler being correct. In particular, since they're writing proofs using the semantics of the Juvix core language, if the Juvix compiler somehow does not correctly translate those semantics to the semantics of Michelson execution, the proofs aren't going to apply. So the sort of advantage of this approach is that it's expressive and can be much more developer-friendly than writing proofs about, say, Michelson or some other backend directly, but it introduces a dependence upon the correctness of the compiler. So if you are particularly worried about that, one approach is to write, say, proofs both in Juvix and then also write some proofs using Micho Coq or something like that for the output Michelson code. Now, the other challenge in compiling a high-level language to a low-level or lower-level virtual machine backend is that the user who's writing programs is also somewhat abstracted away from the underlying costs. So if you're writing Michelson directly, the instructions you're writing correspond to the gas cost you're paying. But if you're writing in Juvix, there are many, many layers of compiler transformations, and one line of Juvix might correspond to a dozen Michelson instructions, or it might correspond to a multiplication of the number of Michelson instructions, depending on what that line is doing, say, higher order function calls. So we've tried to mitigate this as much as possible in Juvix, both by writing a full stack compiler, using zero cost abstractions when possible, but also by using quantitative type theory, which is a recent flavor of dependent type theory, or so to speak, that introduces very precise usage quantization. This means that the compiler can check and in some cases infer exact usages of variables throughout a program, which means that we get a kind of, you can think of it as a kind of linearity, but it's very general. And I'll talk about it in more details in further slides. But that allows the Juvix compiler to use that usage information to perform far fewer stack operations in Michelson. So we hope that that combination is enough for people to actually be able to write contracts in Juvix that are pretty performant in the backend. First question from the audience. So for a language to allow formal proving, do you need this language to have the feature types depend on terms? Not necessarily. Formal verification can mean many different things to many different people. It's kind of, just like blockchain means many different things to many different people. It's a sufficiently buzzwordy term that it has lost a discernibly specific meaning. Dependent types are a very powerful form of verification, you could say. They're very expressive, and they can be very, types, the theorems are very terse. So you can write like a type like supply conservation for your contract, and the term which inhabits that, the proof, might be pretty complex. Like you might have a lot of different execution pathways in your token contract, but what you actually care about, what a user is going to care about, is that some term inhabits that type, because that guarantees that the thing they want, which is supply conservation, is satisfied. So in that sense, dependent types are quite nice. But they also in some ways they can be more complex to use maybe than some other kinds of formal verification, or they are, it's not possible to automate them, for example. So you could have a less expressive formal verification, but which you could always just check. And in dependent types, it's not the case. You need to write proofs. Hope that answers the question. So the compiler architecture of Juvix, which I'll go over next, includes a front-end language, which is compiled to a core language in type theory, then swappable backends. And so far, we've focused mostly on the Michelson backend, but we've also started work on an arithmetic circuit backend for compiling Juvix to circuits with which one could write snark proofs. And I'll talk about that briefly towards the end of the presentation. Another thing to note in the compiler architecture of Juvix is that we have architected it for multi-backend support, and specifically what I mean by that is that users will be able to write contracts in Juvix in the front-end language, that parts of those contracts will be compiled to different backends. So this is particularly relevant when you are, say, talking about a Gestalt system of smart contracts, which includes both Michelson code executing on Tezos and, say, zero-knowledge proofs being verified. So you want, as the author of the contract, as the developer, you want to reason about the behavior of your system as a whole. So it makes sense to write one contract and then compile different parts, one part, say, to a circuit and one part to Michelson. And the fact that that's done in the language means that we can type check across this backend boundary, and we can do like automatic binary conversion, this sort of thing. All of that plumbing, for the circuit backend is of course not written yet, and the circuit backend will be most useful once the BLS 12381 opcodes are added to Tezos in an upcoming protocol upgrade. But architecturally, we've designed Juvix to make that possible. So the front-end language of Juvix is only one slide, and it's only one slide in this presentation because the front-end language of Juvix is not intended to be innovative. It uses a syntax which is inspired by ML mostly. Has functions, data types, pattern matching, denotation, first-class modules, and coming soon, type classes, pretty much in the format you would expect. You can find syntax examples in the repository and on the website, and it's all distributed to Juvix core where the type checking happens. Juvix does not intend, the only thing which is like pretty much different about the syntax, the front-end language than what you've seen before, is that it includes these usage annotations for quantitative type theory. But in general, this is not an area in which we're intending to innovate. We want it to be familiar to developers, and the syntax of ML or modern functional languages is quite sufficient for our needs. So now getting into the interesting bits, core quantitative type theory. So Juvix uses a type theory, which I guess informally is called quantitative type theory after the second paper here, which is based on two papers. The first, I Got Plenty of Nuttin by Connor McBride, and the second, The Syntax and Semantics of Quantitative Type Theory by Robert Atke, and extended with practical things. But the main novel bit is this quantization. So this quantization allows Juvix to track, or allows a type checker to track usages of variables in the program. So think of a usage as a sort of a measure of the computational usage or the computational consumption of a term. So the type theory is generalized over a semi-ring, but Juvix, if you want a good intuition for this, you can think about just like when you're actually executing the program, how many times is this term going to be computed? So if I have some variable, if I say I have x equals 5, and then I use x in a function once, then x is used once, so the usage is 1. But let's say I use x in a function twice, then the usage of x needs to be 2. I need to produce 2 copies, and I'll consume 1 copy in the first function call and the second copy in the second function call. So it's a kind of generalized linearity if you've used a language like Rust before, or if you've used linearity extensions in functional languages like Haskell. It's like a generalized version of that. So quantitative type theory needs to be instantiated over a semi-ring, which has the usual semi-ring things. You could choose the semi-ring of Booleans, in which case terms are either computed or contemplated, or you could choose the semi-ring of 0, 1, or many. That's what interest 2, which also uses a slightly differently flavored, but an extended version of quantitative type theory uses. You could use the semi-ring of natural numbers, or you could use the semi-ring of natural numbers plus omega. which is the most expressive option, and that's what Juvix uses. So omega here means any number of usages. So you could have a variable which is used 0 times, 1 time, twice, 356 times, or omega any number of times. And if you look then at what judgments look like in this type theory, they're like regular typing judgment, except that they have this annotation here, row underscore 1 through row underscore m and sigma. And this is seems like maybe extra useless accounting from the perspective of the type theory, but where it's really useful is when you compile it down to various backends, both in that you can erase terms which are not computed over at all, and in that you can you have precise usage information for terms which are computed with that you can use to optimize the output code you're producing. So just to quickly illustrate how this works, I want to talk mostly about the usage accounting rules for lambdas and applications. So in the typing rule for lambdas, if you need some number of usages of a particular argument to compute some function, then you annotate in the type of the lambda, you annotate this argument here, it's x, with the required number of usages pi. And then when you apply that function in the lower rule here, you will need to produce that number of usages of the argument in order to compute the function. So here, this is represented in the bottom of the judgment by the multiplication of the second context by pi. And this means that you are basically accounting for whatever was also dependent on whatever you previously required in the context to produce that variable. So you multiply things through and end up with accurate accounting for whatever you're going to need to compute. Now it can be computed, and this doesn't quantitative type theory doesn't have a particular computational paradigm, or so to speak. You don't need to interpret it in any particular way. This just will measure in some term the number of types of variables used, and then that information can be used by the backend of your compiler as you please. So some concrete examples which might help illustrate this. Top of the SKI combinators, if you're familiar with those, but mostly I'll just talk here about church-encoded natural numbers. So church-encoded natural numbers in type lambda calculus here are as normal, except that we have these annotations. So here we're typing just one usage of the church-encoded natural numbers. That's the first annotation, 1, but then we require n usages of the successor function, and that corresponds to the usage n of s. And we just need one usage of z. So that will mean that the types for different church-encoded natural numbers are actually different in quantitative type theory, where they would be identical in general, because this annotation n will change depending on the number. So what does this quantization allow us to do? This quantization has two main advantages. It allows us to completely erase what we call the contemplated fragment. So the contemplated fragment consists of everything which is annotated with 0 usages. And this basically is going to be proofs. So if you're writing a bunch of proofs in Juvix, you can write them in a fashion where they're sort of external, where you have one program and then you write separate proofs about it, or you can write them in a fashion where they're internal, where you're passing around proofs and data structures. Either way, as long as they're in the 0 usage fragment, they can be completely erased at runtime because after this quantization check, the type checker knows that it doesn't need to compute over these terms, and so it can just get rid of them, and they never incur any runtime cost. So how do we do this? The only complex bits here are the lambda and application rules. Those are the ones I'll go over. In the lambda rule, basically, if we have a lambda function which takes some 0 usage, which doesn't actually use its argument, or the final result is in the 0 usage fragment, then we can erase the erase the lambda altogether and just use the body. And if we have an application of a lambda to a 0 usage argument, we erase the application, and those match up. So I won't go through the proof in this presentation, but if you reason about, you could think of it as like sort of matching parentheses or something, very abstractly. If you reason about going through your term, you will end up having erased a lambda that corresponded to a 0 usage argument and having erased the application because you were applying it to something which the type here are checked those match, and you end up not needing to perform any computation at all. So that's all well and good, but in practice, this quantitative set theory does run into a problem, or at least a limitation, in how much usage information we can actually produce. And that is that usages are often not so simple. If we are thinking about a smart contract, which is doing a lot of different things, that smart contract is a function, and probably the usages are going to vary based on what actual execution path is taken. So another way of phrasing that is that the usages of some subsequent arguments to a function will probably depend on the value of previous ones. And in pure unmodified quantitative type theory, there's no way to express that because usages are just on the semi-ring. So we can't capture the fact that if the first argument of the function is true, the second argument is used once, and if the first argument is false, the second argument is not used at all. But we'd like to be able to capture that because it would allow us to produce more efficient output code. So we've also been working on what we call first-class usages, which is a way to lift usages, crazily enough, into the dependent type theory itself, such that usages can be cast to and from terms, and then the usual dependent type machinery can be used to express usages which are dependent on terms. So you can have a usage of the second argument to your function, which is dependent on the value of the first argument, which is exactly what we want, and the type checker can check that, and backends can make use of it. At the moment, we're working on formalizing this before we deploy it. So now I want to talk about the Michelson backend, how we compile to Michelson, and how we utilize this usage information. Most of you are probably pretty familiar with Michelson, so I won't talk about it too much. But Michelson is a stack-based smart contract VM used by Tezos. It has relatively high-level data types, set, map, etc., primitive functions, a series of instructions. Each instruction corresponds to a state transition rule, and according to that state transition rule, the interpreter rewrites the stack. Michelson is statically type-checked, but the static type checking used by Michelson just verifies executability. So it verifies that the stack types of these instructions, which all have input and output stack types, are correct throughout the program. It does not verify semantic correctness. So Juvix is focused on verifying semantic correctness. Now, in compiling to the stack machine, we need to do a few things. We need to do the sort of simple accounting to track a virtual symbolic stack, mapping variable names to stack positions, so that while we're compiling, the compiler knows when the user refers to a variable by name, the compiler keeps track of where that variable actually is on the stack. So in a very simple case, before we introduce usages or quantization into this, in a simple case, if we have some two-argument function called f, and it takes its arguments x and y and multiplies them, then the compiler will compile that to a series of instructions which fetches x and y from their positions in the stack. Then the compiler will inline the body of f, which in this case is just the multiplication instruction. And that will result, for example, in this Michelson instruction sequence here, Doug3, dupe, dig4, Doug5, dupe, dig6, mul. Now, you'll notice that we're doing this duplication. And this duplication is necessary in the naive model without detailed usage information because these arguments might be used elsewhere. We're applying f to some x and some y, and who knows where those are used elsewhere in the program. At this point, we don't have any information about that, so we have to duplicate them and leave them where they are. Or we can move them, but we have to keep around a copy. We can't just consume them. Another thing to note is that in Michelson, lambdas are expensive. So if you have a higher order functional language where people are passing functions around all the time, and you compile them all to Michelson lambdas, your contract would be oh so terribly slow. So in order to mitigate this, the Michelson backend of Juvix tracks partially applied functions, and it does not immediately compile them to lambdas. It instead sort of keeps around the curried functions and only produces one or maybe a few lambdas at the end of the compilation process. So now we've got all this fancy usage information. What can we do with it? Well, with usage information, we know how many times each variable is used. So we adjust the virtual stack model we're using, and instead of just tracking a mapping from the name of a variable to its position on the virtual stack, we also track the current usage information. So when a variable is introduced, according to its usage annotation, we add it to the virtual stack with that number of usages, and when usages are consumed, we decrement the number of usages. So if we take the identity function, f of x equals x, without usage information, that argument must be duplicated when we compile it. But if we know that the argument is only used once, we can simply move it. And in a more complex example, if we have some square function which needs 2 usages, then we can both catch the variable lookup and we can ensure that we only need to duplicate the minimum number of times. So this doesn't cover everything. It certainly helps a lot in terms of the output code produced in terms of minimizing stack operations, but we're also working on ANF, which will move things around such that all functions take primitives, enabling some more stack-based optimizations. And as soon as first-class usages are theoretically sound enough to implement, we will also add support for those in our Michelson backend. Arithmetic circuit backend. So I'll just talk about this quickly. You could find out more information on the resource links, which I referenced at the end of the presentation. The arithmetic circuit backend is our attempt to bring proofs to zero-knowledge circuits. Zero-knowledge circuits are useful for privacy and computational compression, but they are also, similarly to smart contracts, finicky and bug-prone. They kind of have to operate with all these weird field elements. You want them to be super optimal, so you have optimizations in different places. They would greatly benefit from proofs. So our idea here is to compile a sort of a restricted set of Juvix terms to circuits directly. And that means that users need to write a validity predicate, so in correspondence with the circuit, which is taking some public and private input and either returning true or false. The users will write a function in Juvix that looks like that, and then the arithmetic circuit backend compiles that to a circuit. Now, this is, of course, limited because it's a circuit, so everything is inlined. You can't lay Frontend lambdas around, but you can use data structures, you could use abstraction, all of the nice stuff, and you could prove properties of this validity predicate function in Juvix, which is quite convenient. We're also working on an integration of the circuit backend with this proof system Plunk, which is sort of emerging as a standard of the CKP ecosystem. And in particular, the integration of plookup brings lookup tables, which makes bit twiddling, for example, in hash function permutation rounds, much more efficient. And here we're working on a standardized IR for Plunk and plookup that the Juvix backend can target, and that the proof system can also sort of update its backend over time to more efficiently encode things represented in that IR. So the final bit I want to talk about here is proof UX. This is really important. Dependently typed languages are hard for users to write proofs in. And if, no matter how expressive the proof system is, no matter how efficient the compiler is, if it's too hard to write proofs, we think that will probably be a barrier that will prevent people from actually using Juvix or actually writing, actually getting more more assured or higher assurance smart contracts out of their usage of Juvix. So we've been doing a bunch of research into how we can improve the UX of developers who are writing proofs. Now, in independently typed languages, there are kind of 2 styles of proofs. One is referred to as internal verification. And internal verification means you sort of mix proofs and data. So you have kind of correct by construction data types. The other is external verification. In external verification, you write a sort of normal, probably not dependently typed, or at least not with proofs, a program, and then you have separate proofs of properties of that program. Like you have a contract function, you have separate proofs of properties of the contract function. And we're focusing a little more on the latter because we think it's closer to the development process, which people will go through when they write smart contracts. They'll probably first want to prototype, then want to write proofs before they deploy in production, and because it is a little more amenable to the kind of partial automation we want to do. So there are already a lot of nice, helpful automated proof search technologies which exist, like sort of proof search and Agda, if you use the auto keyword. I think Coq has some similar provisions, or an SMT solver. But of course, because dependent types are very expressive and quite general, these automated search technologies may never find a solution. So often you need to write manually using tactics or using sort of stepping through rewrites. You need to manually write a proof. So we've chosen to focus on external verification, and rather than engineering a new magic proof search technology ourselves, at least not yet, we've chosen to focus on allowing the user to mix and match the ones which exist to select the best option for their contract and to use them in combination. So what does this look like? We've been doing research on our algebraic effects system, which we call Which. I'm just going to switch to the diagram here. I hope you can read this text, but the most helpful part to look at is the center. So Which is a way to use algebraic effects to combine different techniques together, including in proofs for the same function. So if you look here, we're talking about commutativity of addition, and you can see here that in one case of this proof, we're simply using a tactic with a ring solver, and in another case of this proof, we're actually using search. So then, because we're dealing with, because we're abstracting this in an effect system, oh, you can't really read the text. Apologies. It is linked at the end. But the important part to cover with which is that you could chain these handlers together, like a monadic effects. So you could solve part of your proof with tactics, or simplify it a bit with tactics, and then use search to get to the end goal. Or you could use search for some intermediary goal, and then use tactics to get to the end, chain them together in arbitrarily complex patterns. And of course, sometimes that will result in errors, so we're also working on ways to helpfully display internal state to the user when they don't successfully write the proof. Cool. Project status. What currently is Juvix looking like? So there's a lot of research and implementation work here. We want to produce a production-ready language, but we also want to have the requisite theoretical background in design, design considerations such that the language we produce is a substantial step forward in terms of the security of the smart contracts and performance of the smart contracts people actually write. Juvix is in what I would call a developer previewable stage. So we would not advise you to write production Michelson smart contracts using Juvix. Like I mentioned, correctness is going to depend on the correctness of the compiler semantics, and we'd like Juvix to see some more testing before it's used for production. Unless you're planning on verifying the output with Micho Coq, in which case go right ahead. But by component specifically, the front-end language is basically fully functional, except for some advanced features such as more advanced versions of first-class modules and type classes. So you can already write in syntax. There's also a full grammar provided in the repository. The core quantitative type theory is theorized and implemented over the semi-ring of the natural numbers plus omega, and we're working on a formalization of the first-class usage extension in Agda, which we'll try to finish up before we implement that. The Michelson backend is functional. We're currently working on some performance optimizations to better compile key splits in the data type system, but simple contracts work just fine. With the arithmetic circuit backend, the MVP is complete, but that may not be so useful. In any case, you probably want to wait until BLS 12.381 opcodes are deployed to Tezos, and in coordination with the cryptography team on Metastate, we're also working on integration with Plookup, which will produce much faster output circuits than the current method. So suggest looking at that. And I will note that Plookup, so we're working on this, but that Plookup is a proof system, so it doesn't require a Tezos upgrade. You will need to, if your users are, say, creating proofs as they interact with their smart contract, those users will need to somehow download the proof system code to create the proofs. But the verifier, it will be possible to write a Michelson contract verifier as soon as we have the BLS 12.381 upcodes. Tezos doesn't need to upgrade specifically to support this proof system. Proof UX, we have an initial implementation in Agda, and we're working on integration with the Juvix code base. Where to go if you want to find out more, look into the code, look into the theory, ask questions. The website, which a slight refactor of is coming soon, at the moment is pretty simple, but it's juvix.org. The primary repository and ProofUX repository you can both find on Metastate's GitHub. All of our blog posts about Juvix are on Metastate's research blog. And there are 2 forthcoming papers, compiling quantitative type theory to Michelson for compile-time verification and runtime efficiency in Juvix, which is forthcoming in ISOLA 2020. That will be published soon. That talks mostly about the core type theory, the quantization, and the Michelson backend. So if you're interested in the details of those, I suggest consulting that paper. And towards user-friendliness and proof assistance, automated strategies via algebraic effects and handlers. That talks about the which algebraic effect system, the rationale behind it in more detail than I've outlined, and the mechanism by which it is implemented. And that's forthcoming in HATRA 2020, also pretty soon. You are more than welcome to email me anytime, cwgoes@cryptium.ch. And now I think I would love to take questions.
Okay, so thank you for this interesting presentation. So we have received lots of questions for the audience, so I'll just read some of them out.
Yes.
So first of all, why did you go with dependent types in particular? What would be the problem with a system like HOL?
Why dependent types in particular? It is more, well, one, we wanted to work specifically with this quantitative type theory, which melds dependent types and quantization tracking. Potentially, there are also ways of integrating this kind of quantization tracking with HOL, though I'm not super familiar with it. And two, we think that the kind of, if you want to write like, say, particularly complex proofs of smart contracts, there's more prior work to draw from Koch, from Agder, from Idris, this kind of proof UX work we're doing in terms of actually making it sort of possible to write those proofs, because they require a combination of manual techniques and automatic search.
Mm-hmm. Okay. So another question. Usually type classes and modules are not thought to play very well together. How do you plan to get around this?
Yes, that's true. And there will be, it will not be possible to perform also dependent types make type classes more complicated as well. So it will not be completely possible to perform the same kind of automatic type class resolution like happens in Haskell. In Juvix, sometimes you will need to specify which type class instance you want to use. And there will be some restrictions on how first class modules interact with type classes.
Okay.
But generally, it just results in the programmer needing to be slightly more verbose, which is maybe less concerning when you're talking about smart contracts, because usually the programs which you're dealing with are relatively small. And being more verbose is an acceptable cost to pay.
Okay, so here's a question. So imagine there is a proof of false in Juvix. Unfortunately, that kind of bad surprise can happen. Would it be exploitable by blockchain attackers?
So that depends on what, I mean, a proof of false in Juvix in isolation is unrelated to any blockchain. But if people are using Juvix to verify their contracts and there's a proof of false in Juvix, so a bug in the type theory, then verification performed in Juvix would not be accurate because anyone could have used that proof. So if you read the proof, you can figure out whether it's exploiting this or not. But if you don't read the proof, if you just check it using the type checker, that could be exploited. Now, this can be mitigated by also checking your Michelson contract with Michel Koch, for example. And we are working on operational semantics for the Juvix language, which will check the sum properties of consistency, soundness of Juvix in an existing proof system. So we can kind of bootstrap it that way.
Okay. So two questions on this. So first of all, I mean, this whole approach to correctness relies on the fact or the ambition that your compiler is correct.
Yes.
But your language is quite high level with lots of features and quite rich theory. So you need a lot of confidence to use your language instead of verifying the compiled bytecode directly. So along with this question, I'd like to piggyback also the question whether you considered targeting the Albert language instead of Michelson, which would allow you to at least have one stage of the compilations which will be certified eventually.
Yes, we have considered that, and we may do it in the future. We sort of already started on the Michelson backend and wanted to get that to production, but I absolutely agree that the more we can reduce the correctness reliance on the Juvix compiler, the better. Is the Albert are the semantic transformations performed by Albert like verified or formalized?
They will be.
They will be. All right.
The plan.
Well, maybe we can split our efforts here. That would be fantastic.
Yeah, that's the idea of the project. Okay. So another question. In the example of church encoded natural numbers, where is n bound? So okay, maybe you can go back to that slide.
Yeah, 1 second. Example of church encoded natural numbers. This is a little lazy. N is not bound. I just mean that if you're encoding some church number n, the usage annotation on S will be n. If we were operating in the in the first class usage, version, then n would be bound with an additional lambda.
Okay. Do you have any slide with some example programs you could show?
No, I don't. Apologies, but we do have example programs. I can send you links to them. Is the Juvix?
Okay.
Sorry.
Go ahead.
Just reading the next question. Is the Juvix compiler implemented in such a way that it can be ultimately be verified? What's the implementation technology? The Juvix compiler is implemented in Haskell. So there are some efforts to add dependent types to Haskell itself, which could be interesting. At the moment, we're working on a separate formalization of the operational semantics in Agda.
I guess you could use, there's something like Coq of Haskell, similar tool that you could use to translate your whole code base to Coq and then...
That's right.
Have fun.
We considered writing the compiler directly in Coq or Agda. It imposes a lot of performance penalties.
Okay, so I think for now we've run out of questions from the audience. So maybe I can ask a small question.
Yeah.
So what I'm thinking is that, so now if you write a contract in Juvix and you want to verify it, so typically when you verify something non-trivial, then you would love to have a large database of already proven facts and theorems. But I assume that here, since you're starting off from scratch, there won't be such a database. Is that correct?
Well, so when you're compiling to Michelson, because Michelson already has sort of mid-level or high-level data structures and more complex primitive operations, we basically have to build in properties of those primitive operations, or like the fact that addition in Michelson is commutative. That we can't prove that in Juvix because it's primitive. So we have to take that as a built-in property of the addition function for the Michelson library in Juvix. So in that sense, there's some basis. We have to make sure, of course, that all those properties, built-in properties, we're assuming are actually correct. Then, I mean, it's pretty straightforward. We haven't written too much of a Juvix standard library yet, but we're working on it, and it's pretty straightforward to translate existing code from Coq, Agda, Idris to that. So yeah, that will need to be built up for time, absolutely.
Okay, so I think we're done. There's no more questions from the audience. So I would like to thank you for your presentations and for answering all the questions. Okay, here's a quick question. You mentioned possibly providing high-level automation mechanism like SMT solvers, etc. Is there an SMT solver you're interfacing into Juvix? How are proofs done? Is it more the Agda style, or is there a Juvix tactic language in the manner of Coq? So that's a lot of questions at once.
That is a lot of questions. We're working on a simple tactics language. More details of that are outlined in the paper on which. In terms of specific SMT solvers, we'll probably integrate C3, at least first. Although I'm open to suggestions, SMT solvers are not my area of expertise. So if you were working on a better one, please let me know. What was the third question?
How are proofs done? Is it more Agda style, or is there a Juvix tactic language like in Coq?
It's mixed. I mean, and because of, so if I go to this example here, it's probably a little bit closer to Agda than Coq, but you also have this effect syntax and are using potentially different search tools or tactics at the same time and combining them together. So sort of a flavor all its own. Hopefully that will be intelligible. But our goal is to reduce the number of lines that developers have to write proofs. So if you can conduct part of it via search and part of it via tactics or manual rewrites, in our mind, that's a win.
Yes, you'll make developers happy by making them work less. Okay, so I think this wraps up today's session. So thank you again, Christopher, for your talk and taking the time. So the next seminar will be with Raphaël Cauderlier that will present Michocoq, a formalization of Michelson in the coq proof assistant. So hope to see you there.